Hello, dear student. Now I am going to discuss with you today chapter number 14, Semiconductor, Electronics, Material, Device and Simple Circuit. It is a very important for your exam. I will discuss with you some important questions and some important lines. बेटा अब सीबीएसई क्वेश्चंस आपसे अराइज करेगी वो कॉम्पिटेंसी बेस्ड क्वेश्चन होंगे. तो फर्स्ट ऑफ ऑल यू नो द होल कंसेप्ट इन दिस चैप्टर. Now, introduction of this chapter. In 1897, invention of vacuum tube by J. A. Fleming, and 1906, invention of vacuum triode by Lee D. Forrest. Subsequently, introduced the vacuum triode and pentoid tube. Vacuum tube device are bulky, consume high power, operate generally at a high voltage 100 volt and have the limited life and low reliability. Now, 1939 invention of semiconductor diode by Russello, and 1943 the world first computer ENIAC. It is occupied an area around 1800 square feet. It had 18,000 vacuum tube and the weight around 50 tons. In 1948, invention of semiconductor transistor by Bradin, Breton and the Shockley. In 1956, Nobel Prize. 1958, invention of integrated circuit IC. Atoms. When the million of atoms brought close to each other, valence orbit and the unoccupied orbit are split according to the number of atoms. In this case, the energy level will be closely spaced and will be difficult to differentiate the orbits of one atom from the other, and they look like a band as shown in figure. The range of energy possessed by the electron in a solid is called energy band. So what is the energy band? But the range of energy possessed by the electrons in a solid is called the energy band. Solid of magnesium having an atom. Conduction band, but this region for conduction band. Here is valence band and full fill 3s band. A block of magnesium metal of an atom. ये पूरा स्ट्रक्चर बेटा मैग्नीशियम ऑफ एन एटम का. ये 4s बैंड 2n, 3p band 6n, 3s band 2n, 2p band 6n, 2s band 2n and first band for 2n. Now what is, I'm going to discuss with you what is the valence band. Okay, so valence band, it is the highest occupied energy band at absolute zero temperature in insulator and semiconductor. It is a completely filled. In a metals, it is a partially filled overlap with the conduction band, allowing the electron movement. Now, next, I'm going to discuss with you what is the concept of conduction band. It is the next higher the band above the valence band, जिन्हें आपने देखा ऊपर, in insulator and the semiconductor. It is empty at the absolute zero and it is separated by a band gap with valence band. It metals either the conduction band overlap with the valence band or the valence band itself partially filled with act as a conduction band. Now next concept, what is energy band gap? So beta, the gap between the top of the valence band and the bottom of the conduction band is called the energy band gap. Energy gap represented by Eg. It may be large, small or zero depending upon the material. Now next, I am going to discuss with you what is energy gap. So I have already discussed with you energy gap. Classification of the material on the basis of conductivity. But of first, conductor, semiconductor and insulator. They possess by low resistivity or high conductivity. So rho approx 10 to power minus 2 to 10 to power minus 8 ohm meter, approx 10 to power 2 into 2 10 to power 8 says meter inverse. Now semiconductor, they have the resistivity of conductivity intermediate to the metal and insulator. Rho approx 10 to power minus 5 to 10 to power 6 ohm meter, and insulator they are have high resistivity, low conductivity. Rho approx 10 to power 11 to 10 to power 19 ohm meter. Now next concept is energy band in metal, insulator and semiconductor. I'm going to discuss with you energy band in metal, insulator and semiconductor. So first of all, I will discuss with you concept of metal. There are two main types of band structure in the metal. First one is partially filled. Partially filled. Here is graph diagram for partially filled. ठीक है, empty of three band. The highest occupied energy band, valence band, is not completely filled and act as the conduction band. So electrons are freely to move within the band. Sodium, copper. Now, second is overlapping band. The valence band and the conduction band overlap, eliminating any band gap. Magnesium. So diagram for energy band in magnesium metal, completely empty, completely filled, filled to be valence electrons. Now next, uh, what is insulator? Now next concept for insulator, the valence band is completely filled at zero and the conduction band is completely empty, absolute zero, separated by a large energy gap EV greater than 3 volt. Now this is for insulator. Now, what is a semiconductor? Now, for semiconductor have an energy band structure similar to the insulator, but with a smaller band gap at a absolute zero. It has a completely filled valence band and completely empty conduction band. That is the at the absolute zero, it behaves like a insulator. Because of the small band gap at room temperature, some electron from the valence band can acquire enough energy to cross the energy gap and enter the conduction band. This electron through in small numbers can move in the conduction band, and hence the resistance of semiconductor is lower than the insulator. So here is energy gap is less than 3 electron volt. Now I am going to discuss with you classification of semiconductor. Now first is intrinsic semiconductor. What is the concept for intrinsic semiconductor? And semiconductor is its purest form is called an intrinsic semiconductor. It conducts electricity due to the thermal excited electron and holes. Now, schematic representation of the intrinsic germanium crystal and it's the band diagram at absolute zero temperature. Now, here is germanium in outermost self, 1, 2, 3, 4 electron of sharing pairing at 0 Kelvin. Conduction band here is energy gap between here. Now an intrinsic semiconductor behaves like an as an insulator at 0 Kelvin, temperature at 0 Kelvin. Now next, a schematic representation of an intrinsic germanium crystal and its band diagram. Temperature is positive greater than 0 degree. Here is positive temperature, conduction band, here is valence band. For note, as the temperature increases, these electrons get more thermal energy, break away the covalent bonds and becomes free electron contributing the conduction band. And these free electron with large electron leaves a valence with an electric charge positive E in balance with the effective positive electronic charge is called a hole. In intrinsic semiconductor, the number of free electron n equal to the number of hole. Here is number of electron is equal to number of hole for intrinsic semiconductor. The total current I, thus the sum of the electron IE, the whole IH is equal to IE plus IH. Now I am going to discuss with you one question from NCERT. वेरी ये बहुत पॉपुलर क्वेश्चन है बेटा एनसीईआरटी का सी ठीक है कार्बन सिलिकॉन एंड द जर्मेनियम हैव सेम लैटिस स्ट्रक्चर why is carbon is insulator while Si and Z means silicon and germanium intrinsic semiconductor. Very important question for you. Now, the four bonding electron of C, Si or germanium lie respectively in the second, third and fourth orbit, and hence energy required to take out the electron from these atom ionization energy EV will be least for Ze and followed by silicon and highest for carbon, and hence number of the free electron for conduction in germanium and silicon are significant but the negligible small for carbon. नाउ व्हाट इज द कंसेप्ट ऑफ डोपिंग बेटा हम लोग देखेंगे कंसेप्ट क्या होती है डोपिंग डोपिंग इट इज द प्रोसेस of adding the impurities to the increase the conductivity of a semiconductor. The impurity atoms are called डोपेंट्स। ठीक है, अब आते हैं सेकंड क्या होती है हमारी एक्सटेंसिंग सेमीकंडक्टर। एक्सटेंसिंग सेमीकंडक्टर आर डोप्ड सेमीकंडक्टर depending on the two types of impurities added. There are two types of semiconductor, like first n type semiconductor pentavalent doping and p type semiconductor trivalent doping. Now first n type semiconductor, it is obtained by doping an intrinsic semiconductor germanium or silicon with pentavalent atoms like arsenic, SbP, etc. Now schematic representation of the n-type S silicon crystal and its band diagram is given here. A very note important point here, the pentavalent dopant is doping one extra electron for the conduction and hence is known as the donor impurity. The donor impurity becomes positive. In n type of semiconductor, the total number of conduction electron Ne is due to the electron contributed by the donor and those generated intrinsically, while the total number of hole NH is only due to the hole intrinsically. Therefore, the electron are majority carrier in n-type semiconductor. Therefore, Ne much greater than NH. Though the net charge of an n-type semiconductor is neutral, since the total number of positive charge hole and positive donor and total number of negative charge electron are same. Now, p-type semiconductor, it is obtained by doping an intrinsic semiconductor germanium or silicon with the trivalent atom like B, Al in etc. Now, schematic representation of p-type of silicon crystal and its Venn diagram is given here. Energy Venn diagram of p-type of semiconductor and p-type of semiconductor also here. Here is energy diagram. A very important and note point here. Here are valency of electron, here, valency of electrons create a hole as the trivalent impurities become the electric effectively negatively charged. The trivalent dopant is the accepting one electron or conduction and hence is known as the donor impurity. The acceptor impurity becomes negative ion. In p-type semiconductor, the total number of hole is due to the hole contributed by the acceptor and those generated intrinsically, while the total number of the electron is only due to the electron intrinsically. Now next, therefore the hole are majority carrier in a p-type semiconductor. Now NH is greater than Ne. Though the net charge of p-type semiconductor is neutral, since the total number of positive charge holes and total number of negative charge electron and negative acceptor ion are same here. Now next concept p-n junction diode. Here is diagram beta. This region is called depletion layer for n type, depletion layer for p type. Number of here is donor and number of acceptor. Neutral p region, here is neutral n region for connected with battery. A p-n junction can be formed by adding a small quantity of pentavalent impurity to a p-type semiconductor or by adding a small quantity of trivalent impurity to n-type semiconductor. Two important processes occur during the formation of a p-n junction: diffusion and drift. So what is diffusion? I am going to discuss with you what is diffusion. So listen, uh, the hole diffuse from p side to n side and the electron diffuse from n side to p side. This motion of charge carrier gives rise to the diffusion current across the junction. Due to diffusion, a layer of positive charge is developed on n side of the junction and a layer of negative charge is developed on the p side of the junction. Okay. Now next, what is the depletion layer? The space charge on either side of the junction together is known as depletion region. The depletion layer consists immovable ions hole. Now this is responsible for a junction potential barrier. Now second concept is what is drift. So drift, the positive charge of on n side of the junction and negative charge on p side of the junction develop an electric field. Due to this field, an electron majority carrier on p side of the junction move to the n side and whole majority carrier on n side of the junction move to p side. The motion of charge carrier due to of the electric field is called drift. Initially, diffusion of current is large and drift current is small. As the diffusion process continues, the electric field strength increases and hence drift current also increases. This process continues until the diffusion current equals the drift current. Thus, in a PN junction under the equilibrium, there is a no net current. So, there is no net current. Now, barrier potential, here is p type, n type electric field, here is barrier potential. The loss of electron from the n region and the gain of electron by the p region causes a difference of the potential across the junction of the two region. Since this potential tends to prevent the movement of the electron from n region into the p region, it is often is called barrier potential. The barrier potential of a germanium diode is 0.2 when that of the silicon diode is 0.7 volt. Now, semiconductor diode, junction diode, but a symbol of diode, so anode and cathode, P, and here is N type. Okay. Now, PN junction diode under forward wise. Now, I'm going to discuss with you PN junction diode under the forward wise. It is a very important for you. For forward wise, you can see, but here is positive terminal, here is negative terminal, positive connect with P and negative connect with N. In P side of the diode is connected to the positive terminal and N side negative terminal of the battery. It is said to be forward wise. The basic concept for forward wise, you can see, आप ये देखोगे ये आप P टाइप को कनेक्ट करना है बेटा पॉजिटिव टर्मिनल से, N टाइप को you will connect with negative terminal. The direction of the applied voltage V is the opposite to the barrier potential V naught. As a result, the depletion layer width decreases and the barrier height is reduced. The effective barrier height under the forward bias is V naught to V. Now next, at a high applied voltage, electron from N side, electron from N side Electron from N side cross the depletion region and reach the P side. Similarly, hole from the P side cross the junction and the reach N side. This motion of majority carrier on either side gives the diffusion current. The magnitude of current is usually in milliampere. ठीक है, हम लोग मेजर करेंगे बेटा इसमें magnitude of current is milliampere में. Now I'm going to discuss with you PN junction diode under the reverse wise, बेटा just opposite for forward wise. पी साइड आप इधर कनेक्ट करोगे बेटा नेगेटिव से और ये करोगे आप पॉजिटिव से कनेक्ट करोगे. Now, if P side of the diode is connected to the positive terminal and N side negative terminal of the battery, it is set to the forward bias. The direction of the applied voltage V is same as the barrier potential V naught. As a result, the depletion layer width increases and the barrier height is increased. The effective barrier height under the reverse bias V naught plus V. Now, the flow of electron from N to P and the hole from P to N is suppressed. Thus, the diffusion current decreases, okay, enormous compared to the diode under the forward bias. The electric field of the junction is such that the majority carriers are drifted to the majority zone, which give rise to drift current. The drift current is the order of the few microampere. Now, VI characteristics of PN junction diode. Beta, here is P type, here is N type. P N type measure in terms of microammeter, here is milliampere. Okay. Now for forward wise, here is forward wise and here for reverse wise. Now in forward wise, the current first increases very slowly, okay, till the voltage across the diode crosses the certain value. This voltage is called the threshold voltage or cut in the voltage. 0.2 or germanium diode and 0.7 volt for silicon diode. After the threshold voltage, the diode current increases significantly even for a very small increase in the diode bias voltage. For the diode is the reverse bias, the current is very small in microampere, and the almost remain the constant with the change in the bias. It is called reverse saturation current. However, at a very high reverse bias called breakdown voltage V, or the current suddenly increases. The general purpose diode are not used beyond the reverse saturation current region. What is threshold voltage? The forward voltage beyond which the diode current increases significantly is called threshold voltage or cut-on in voltage. Now, what is breakdown voltage? The reverse voltage at which the reverse current increases suddenly is called breakdown voltage. Now I'm going to discuss with you application of PN junction diode. But here is two very important application: rectification. The process of the converting the alternating current to the direct current is called rectification. Now half wave rectification, I am going to discuss with you half wave and full wave rectification. बेटा ये डायग्राम फॉर हाफ वेव रेक्टिफिकेशन, ठीक है। ये आपका बेटा प्राइमरी है और ये सेकेंडरी ट्रांसफार्मर है। आप इनमें देखोगे, आप यहाँ पे आरएल लोड लगा हुआ है और आप जितना भी इनपुट यहाँ पे आपने दिया है और इसका आउटपुट रिजल्ट आपको ये मिल रहा है, ठीक है। फॉर during the positive cycle of input AC and A of the transformer becomes positive and B becomes a negative. So the diode in a forward bias and conduct during the negative cycle of input AC and becomes a negative and B becomes a positive. So the diode is the reverse bias and diode not conduct. ठीक है। The rectifier since the rectified output of this circuit is the only for half input AC wave is called as a half rectifier. Okay. Now next concept I am going to discuss with you, full wave rectifier. Okay. So what is the full wave? Here is AC source, center type of transformer, and here is diode. We are taking here two diode D1 and D2, load RL here. For a full wave rectifier, the secondary of the transformer is provided with a center trapping, and so it is called center tape transformer. During this positive half cycle, diode D1 get forward bias and conduct, while D2 being a reverse bias is not conducting. Hence, we get an output current and output voltage across a load resistor RL. Now, during a negative half cycle, diode D1 would be not conduct, but diode D2 is conduct, giving an output current and output voltage across RL in the same direction as in positive half. Thus, we get the output voltage during both the positive as well as negative half of the cycle. This is the more efficient circuit for the getting the rectified voltage or current than the half wave rectifier. Now, IP and OP wave of full wave rectifier like this, D1 D2 for full wave rectifier, ठीक है। Now diagram here is filter for AC source rectifying, ठीक है, rectifier, ठीक है, RL ruled and DC, totally AC converted into DC in full wave rectifier. Now here is a capacitor is connected in a parallel with the load resistance as shown in figure. Resistance of the capacitor is given by XC is equal to 1 upon C omega. Hence capacitor offers some opposition to the flow of current through it, but DC is omega for 0, and XC is equal to infinity. For this result graph is there. That is, the capacitor behaves as an open circuit for a DC. Therefore, AC component in the output of rectifier passes through the capacitor and very small amount of AC passes through the load, whereas there is no effect on the amount of DC passes through a load resistance. Hence, AC component through load resistance decrease, hence the ripple factor is decreases. Now, but I'm going to discuss with you some previous year question from this chapter. For 1 marks question you can solve for, in which figure is diode used under the forward bias condition. मैंने अभी जस्ट डिस्कस किया है, आप क्या टेस्ट करो, वहां पे टेस्ट करोगे, ठीक है। ड्रॉ द सर्किट डायग्राम फुल वेव रेक्टिफायर, ये भी मैंने क्वेश्चन अभी ऊपर डिस्कस किया है उसके कंसेप्ट को। और एक और क्वेश्चन यहां से बन सकता है बेटा, गिव द क्लासिफिकेशन ऑफ द मटेरियल बेस्ड ऑन द एनर्जी बैंड डायग्राम, डिफरेंशिएट बिटवीन द इंट्रिंसिक और एक्सट्रिंसिक सेमीकंडक्टर। ये बहुत बार एग्जाम में आपके आते हैं क्वेश्चंस। नाउ A very important question, 2003 के क्वेश्चन यहाँ पे बेटा. First question is a rectifier is used for charge AC voltage into DC voltage. With a diagram, explain the working of a full wave rectifier having two diodes. And third, one more question: what is the output frequency of full wave rectifier if the input frequency is 50 hertz? Now, one more question for 3 marks. What is rectifier? Draw the circuit diagram input output waveform of the full wave rectifier. ठीक है. अब आइए एक और क्वेश्चन में बने थे. With the help of a circuit diagram, explain the working of the half wave rectifier. Draw the input and output waveform. So this is all important question from this chapter.